Hello. Oh, we started late tonight. I had to do a little prep work. I wanted to come back to a project that I have not actually been playing with since, gosh, when was the last time? February of this year. There's a couple of ideas that I have that I don't think I can do easily with Swift UI animations, and I've been thinking about turning to the use of shaders to accomplish these visual projects. But here's the kicker: I don't know a whole lot about shaders other than a rudimentary understanding of how to define them, and how to use them in a Swift context, meaning a Swift UI view, using Sprite Kit. Now, this project was built, like I said, many months ago, and just consisted of taking a Swift UI shape, sending it through UI Kit into creating a UI image, using that as a source for a texture, applying a shader to the texture, and then being able to modify it in real time, which has been really fun. It was just a kind of exploration to see what we could do. This is in the same project as the core image filters that been working on, and I'm not quite sure what the status is of this project. As you can see, you've got a bunch of modified and added files to this project under source control that I don't really know if this is what I want to commit. A lot of changes were made as I was just kind of doing some piddling around here. But like, for example, what I had a couple of, what did I have here? So I have a few just images that I threw in here, I think, as these might have been for particle effects, I think. I do have one texture in here, thanks to Two Straws hacking with Swift, made this available. He has a project called Shader Kit, where he's got a few shaders. We used this for, what was it for? For a water effect, which is what you see here on the right. The water effect is being made on an image, and we get to change the different parameters of the shader. We have 3 properties in here, what they're called uniforms. We've got speed, strength, and frequency. I think strength is translated to amplitude here, just how much of an effect we have. And then the frequency is just how rapid the changes happen. And then the speed, how fast to make the water ripple is what these notes say. Frequency, how often ripples are created. Strength or amplitude is how big the waves are. So this is one example of a shader, and I'd like to learn a little bit more about how to create my own shaders, not just use somebody else's, because I've got a couple of specific ideas regarding geometry that I'd like to see if I can put together in a way that's one, reusable, and 2, interesting. So with that, I found a fun little site called thebookofshaders.com. This is, for what I can understand, an ebook that is made available on this website. Go ahead and post this in the chat here. And they've got table of contents seems to be pretty thorough. It says it's a gentle step-by-step guide through the abstract and complex universe of fragment shaders. If anybody has wondered how shaders work or how you might implement them in your projects, I feel like this might be a pretty good resource. I haven't read through all of it, so today's a learning stream for me, and you're welcome to come along for the ride. Might do some gaming towards the end. I'm feeling a little like I want to make some progress with one of many games that are on my list. But for now, I'm gonna just kind of dive into this and let's learn together. Let's have some fun. By the way, if you'd like to follow along in, I don't know what the current state of this is, but let me get my project. Again, I don't know if I actually made it to actually putting shaders in here. Oh yeah, here it is. There it is. So it is available in some iteration. I'm not sure what the the current status is again. I've got a bunch of uncommitted files here, but this is the project on my GitHub if you'd like to take a look as to how I built this. In fact, let me just again get my bearings with what exactly is going on here. We have something called a shader scene. Which again, we're importing Sprite Kit. We are, I've created this type called shader params, which is specifically for this water shader. Again, speed, strength, and frequency. We have an SK scene, which is holding on to an SK shader and SK sprite node, which is initialized on creation here. A couple of methods that are a part of the process for using Sprite Kit scenes. We have a scene did load method, and this is where I say, okay, my background color is clear, my anchor point is set to 0, my scale mode is aspect fit. Again, I don't remember why this is the way it is, but I think I was just following along a tutorial perhaps. Then I have a shader, which is an SK shader, is create water with params of 3, 5, and 5. What does create water look like? Create water looks like this. We've got an array of SK uniforms. So again, Sprite Kit uniforms, which is hard-coded strings. And then we say a shader is equal to SK shader file named SHK water. And again, that's this file right here. And so the idea is that each of our uniforms are prefixed with this U underscore, where we have U underscore frequency, U underscore strength, and U underscore, is it time? Okay, speed, strength, frequency. Where are you, speed? Speed is here, strength is here, frequency is here. And then U underscore time, I don't know what that is. That must be something that's internal to the Sprite Kit, maybe. Because I've also got something called U texture, V color mix. So none of these I've defined in here. This must be something that Sprite Kit understands. You can see here that the only things that we've put in are these hard-coded speed, strength, and frequency, which I guess is used for understanding how to translate these parameters that change in real time. We've got this menu at the top. I have a polygon that I can change the number of sides. Again, this is coming from... Again, we got a shader scene. We have create water. We have did move. We've got update texture image. So this is the incoming image. that's created from our Swift UI view. So let me see where shader scene is used. Again, it's been a while. I'm just getting reacquainted with my project here. Okay, so I have a shader test view and I have a geometry reader. This must be it. This is inside a tab bar application. So if we go to Shader's app, I've got a main menu, navigation lazy view. This must have been before iOS 16. Main menu consists of a tab view of a filter menu for the core image filters, yes. And shader test view for the tab called shaders. Shader test view has 5 state properties. Polygon size, as we see here. Our wave speed, which is a float, wave strength, wave frequency, and we have our shader scene. We make this a state variable, although I wonder if that's actually the right thing to do. Usually when we hold on to reference types, we want to use a state object. And I wonder if back in February, I just was like, oh, I'll just do at state, not understanding that I probably should have a state object. Though there may have been a reason for this, I'm not sure. We'll just trudge through here, just to get a context of what we're working with. We have a linear gradient on the background of a Z stack, so we can just have some pretty colors behind us. We have our controls, which is polygon size, wave speeds, wave strength, wave frequency, where we've got some ranges here. And then we have a vertical stack with text of the original. And then we have our texture view. And look how tiny it is. It's not very big. I wonder if I did that on purpose. Just because we wanted to showcase what's happening here. But it is a little bit smaller than I'd want it to be. I wonder if I would like to have it like more half and half, so I could see what the original looks like and then what the shader applied to it. Let's just take a look. So we've got shader applied. We have our sprite view. Wait a minute. Got our scene. Anytime we change any of these parameters, wave speed, wave strength, or wave frequency, then and also on the polygon sides, we apply a view to the scene here when polygon size changes. That means we're changing our source image. And also when it appears. We update our shader whenever we change any of these parameters. And then that just calls our scene that we're holding on to, and we tell it to update the shader with the params, and then we're applying a new struct. Shader param, speed, strength, and frequency. Kind of want to clean this up a little bit. Maybe I'm becoming less and less inclined to put things on one line, especially when it gets kind of crowded. So for example, just to see, so we can just deconstruct it a little bit. We're updating a shader with the params of this guy. Great. Now, take a look at our texture view. Okay, look, go back to the top. Our vertical stack consists of original and texture view with sides of integer of polygon sides. And texture view is a geometry reader, convex polygon with number of sides, which is an integer, inset by stroke border, line width, dimension times 0.1. Yeah, why are you inset? I don't understand why you're inset. Let's take that out. Let's see what's happening here. Well, I'm gonna have to stop this and rebuild. Yeah, I really don't like how small this is over here. So let's see if we can fix that. Okay, press stop. Maybe if we get rid of the inset, maybe that'll help a little bit. That's weird. That seemed to have affected, so the size of this affected how this was rendered, and maybe it's just the amplitude. It has to be non-zero, doesn't it? Okay. Apply view to scene. Let image equals texture view, which is this guy. So like having a copy of this. Dot UI image. Oh, is it inset so that I can prevent it from having those discontinuities? Maybe that's why. Why did I say dimension times 15%? Let's go back. Okay, yeah, that's what was going on. I was forcing it to be drawn with padding so that I didn't get any strange effects on the borders. Because once this touches the border of the bounds, well, I guess I kind of forced it to not. Okay. So that's where we're currently at with our project. When I say scene update texture image, let's see what happens. We jump on into Sprite Kit. And what we do is we have our UI image. And again, how did we get this image? Let image equals texture view dot UI image. This is a custom method that we've created. This is an extension on view. This creates a UI image out of a view. We utilize a UI window with a frame of some CG rectangle. And then we do our UI hosting controller with the root view, self edges ignoring safe area. This is to fix an iOS 15 bug. Hey, what's up, Crunchy? How you doing tonight? Going back to an old project that I'm trying to resurrect here. We add our sub view, we window make key invisible, and then we say we turn hosting.view.rendered image. Rendered image is an extension on UI view, which utilizes the UI graphics begin image context with options. Gets the current context, renders the layer of the UI image in the context, and then we return the image. And that is how we generate our UI image from our Swift UI view. Looks familiar, yeah. It's been a while since we've looked into this. But my goal today is to kind of dive into the heart of creating our own shaders, because I have a couple of ideas for how what I want to visualize that I just have not been able to get in Swift UI. Notably, there was an effect that I really enjoyed viewing in Lost Ark with the floor doing this really cool like spreading out animation, and you got a bunch of like these hexagons that are shrinking at the same time, and it just becomes like this like diffuse like red colored thing. So I'm trying to see how to create my own. And what's the math behind it? What about I got to do to get that goodness inside these apps? So once we've got our image, our UI image, then we bring this into our sprite kit scene, like so. We create an SK texture based on the image. We then apply that texture to our node, which is again just a SK sprite node that we hold on to the shader scene, and we just say, hey, node.shader is a shader, and that's what gets shown. And every time we change the number of polygon sides, we're recreating that image. And it seems to be pretty fast. Okay, so now that we know what's going on, let's go back to this fun new resource, the bookofshaders.com, which promises a gentle step-by-step guide through the abstract and complex universe of Fragment shaders. So thank you to Patricio, Gonzalez Vivo, and Jen Lowe for this. Let's see. I'm going to move this over here. And what is a shader? Again, this is a learning stream. So I'm getting it. I'm doing a deep dive here. There's probably other resources available that people swear by. I just found one and I'm going with it. Shaders are a set of instructions executed all at once for every single pixel on the screen. That means that the code that you write has to behave differently depending on the position of the pixel on the screen. That makes sense. If you got a big rectangle area, you're going to have a function of your position. So your X's and Y's, probably no Z's because it's a two-dimensional screen, unless you guys are playing with 3D screens. Why are shaders fast? Parallel processing. Okay, so so shaders are preferable when you want high performance output. Video games uses a lot of processing power, and so they got to do a lot of pixel by pixel calculations. So shaders are good for that. This is doing a bunch of this. Okay, so GLSL. Now this is the stuff. GLSL stands for OpenGL Shading Language, which is the specific standard of shader programs that you'll see in the following chapters. We'll work with the OpenGL specs regulated by Khronos Group. Let's take a look at that. What's that? Khronos. Death to Khronos. Oh, by the way, have you guys seen the Hades 2 trailer? Death to Khronos. Probably not this organization. Khronos is the gatekeeper for OpenGL, it looks like. Specifications. So that's neat. The OpenGL specs regulated by Khronos Group. Understanding the history of OpenGL can be helpful for understanding most of its weird conventions. Oh, it's okay. So we're definitely gonna get into some weird stuff. It's also silly. I just learned how the environment variables work and the importance of setting absolute paths to the path environment variable. Hey, that's great to learn. I don't use environment variables very often in my day-to-day, but yeah, that's the kind of stuff that yeah, you gotta once you find that you're using it a lot, definitely good advice. Setting absolute paths. Yeah, for sure. Especially if you're doing searches for like, where is my program? If you've downloaded like a Python script or something, and it's in some weird directory and the computer doesn't know where it is. Yeah, definitely. If you're doing a lot of work on the terminal, then yeah, you'll definitely be using that. All right, so understanding the history can be helpful. Taking a look at this. What is this? Chapter 0, preface. What is OpenGL? Okay. We got a bunch of history here. This is kind of neat. OpenGL, the beginning of the API wars before the dark times. Shaders, OpenGL stagnates, new OpenGL. Bada bang, bada bum. Okay, there we go. So with that, we've already got a couple links here. Why are shaders famously painful? As Uncle Ben said, with great power comes great responsibility, and parallel computation follows this rule. The powerful architectural design of the GPU comes with its own constraints and restrictions. So in order to run in parallel, every thread has to be independent from every other thread. So what this means is it's impossible to check the result of another thread. It's impossible to modify the input data, and it's impossible to pass the outcome of a thread into another thread. So GPU is going to be dealing with all of this. It's got to be blind, and it also has to be memoryless, because the abstraction required to code a general function that changes the result pixel by pixel, depending on its position. The blind and memoryless constraints make shaders not very popular among beginning programmers. That makes sense. Like when I was first learning iOS development, I didn't know like how to deal with shaders. All I knew is that like when I was going through this OpenGL tutorial, I just knew that textures existed, and that they were responsible for dealing with every single vertex in my in all of my points. Does it follow that those of us with little power bear little responsibility? Yes, KNH. I would say that the inverse is true. Absolutely. So yeah, we can go nuts if we don't have very much responsibility. That gives us the opportunity to tinker without worry of repercussion. How you doing tonight, by the way? Good to see you. So they've promised that they're gonna keep things nice and step by step for us here. This is the Hello World example. Okay, what does this triangle do? Oh, we can download the file, the code URL, the artwork URL, artwork to O. I don't know what that does. Usually the Hello World example is the first step, is a simple one-line program. In GPU land, rendering text is complicated. It's too much to do. So instead of Hello World, they're going to choose a bright, welcoming color, which is, let's take a look. We've got an if-def in here. Let's go back to the project. And let's go back to, we have here SKH water. And let's just see what we've got. We got a bunch of notes all the way down here. We don't have any if-defs in here. We just have a void main. This is required for every shader file in order for iOS to play with it. So you got the main here. And we're going to go, oh, hold on. All right. And there they've got it right there, void main. They say a GL frag color for fragment is equal to a vector 4, 1, 0, 1, 1. Now this is interesting. What? Oh, look at that. Very cool. Okay. That's fun. So what this is an interactive editor, which is very helpful. Oh, I'm very excited about this. What does this plus button do? What in the... Oh my gosh. So I just turned this into a Vec 3, and that probably was not a good thing to do. I just messed it up. Uh-oh. Let's go back. Okay, I'm now in real time. Okay, we're back. Careful, because if you do this, things get kind of crazy. I don't know. Must be my browser or something. So this is saying if you're reading this book in a browser, the previous block of code is interactive. That's what they just said. You can click and change any part of the code you want to explore. Changes will be updated immediately thanks to the GPU architecture that compiles and replaces shaders on the fly. Give it a try by changing the values on line 8. Yes, and fortunately, we can do this easier with this tool. We can infer substantial knowledge from these lines of code. Shader language has a single main function, yes, that returns a color at the end. This is similar to C. The final pixel color is assigned to the reserved global variable GL frag color, which means that every single pixel is going to take on this frag color, I guess. Okay. This C-flavored language has built-in variables like GL frag color. And again, we saw this also in here. We have U_time, which I guess is not something that we bring into on our own. VTeX chord is also seems to be built in. The only things that we've defined inside this method, thanks again, Paul, is speed, strength, chord, and then we actually apply, again, there's that GL frag color. You see that? Equals texture 2D, U_texture, comma, chord, which was defined here. And again, this is for every single pixel. So this is going to get called for everything a number of times per second. So it's got to be super fast. So it's getting the sine and the cosine, throwing it into the X and Y. This is a vec2. And then we say texture 2D, U texture, and then it's expecting a vec2. And then he's multiplying it by something called vcolormix.a. I don't know what that is. And that causes us to have a different frag color depending on the offset, which then makes this happen. And that is the wave at work. Very fun. So I'm going to put this back over here and let's just keep going. We've just been introduced to the vec4 that stands for a 4-dimensional vector. Yes. Then we'll see more types like vec3 and vec2. Together with the popular float, int, and bool. Yes, we know these. If we look closely to the vec4 type, we can infer that the 4 arguments respond to the red, green, blue, and alpha channels. Well, there you go. All the way back up here, when this was 1, it was such a, let's try putting it to, oh, if it's 0, then it's, there we go. Okay, we've just demystified it. GL frag color is RGBA. Isn't that fun? Very cool. All right, what else? Is the 4th argument the opacity? Yes, Crunchy. Exactly. That's the opacity. So once we threw it to 0, it's left with the black color, which I guess that means that in OpenGL land, the absence, I guess you don't have a background color unless you specifically place a color underneath. I guess you can't have a clear color. Is that true? I don't know. But I do know that this is full on opacity of 100. This is 50% and so on. Yeah, that's a good question. What does this do? This is just, so you can see that like these RGBA values are going all over the place as we're going out to messing with the color wheel here. That must be the default canvas color. Yeah, that's cool. So that's what the vec4 is for. Where are you at? Okay. What else do we got? Another important C feature is the preprocessor macro. Okay, so the if def and the end if. This is fine. We don't really need to deal with this. I guess, I don't know. I think it's the same support on Mac OS versus iOS. Maybe. I hope. The last and maybe the most important detail is that the GLSL specs don't guarantee that variables will be automatically casted. So automatic casting is not one of them. Oh, I see. So the vec4 has floating point precision, and for that it expects to be assigned with floats. If you want to make good consistent code and not spend hours debugging white screens, get used to putting the point in your floats. This kind of code will not always work. Oh, so 1, 0, 0, 1, you can't do that. You have to have a decimal, is what they're saying. Okay, that's fair. Now that we've described the most relevant elements, it's time to click on the code block, start challenging all that we've learned. Oh boy. You'll note that on errors, the program will fail to compile, showing a white screen. There are some interesting things to try. Replace the flows with integers, and your graphics card may or may not tolerate this behavior. Try commenting out line 8 and not assigning any pixel value to the function. Okay, let's try that. Okay, so a comment. Oh, we see nothing now. Whoop. Okay, go back, and there it is. Let's get rid of the decimal here. In our case, that was fine. It didn't have a problem with it. Okay. So your mileage may vary depending on, I guess, would it be the browser that you use or just the OS? I'm guessing the browser. Okay. Try making a separate function that returns a specific color and use it inside main. As a hint, here's the code for a function that returns a red color. Thank you. All right, I'm going to copy this. Go ahead and throw it in here. And our main, we're going to GL frag color red. Hey, look at that. That's fun. So we can just, what this is showing us is that we can call other functions or methods defined inside the shader code to give us what we want. And so for every pixel, it's just going to return red. Very cool. There are multiple ways of constructing vec4 types. Try to discover other ways. The following is one of them. Vec4 color equals vec4 vec3 101 comma 1. Oh. Okay. Most basic example, you're changing all the pixels inside the canvas to the exact same color. In the following chapter, we will see how to change the pixel colors by using two types of input, space and time. The number of seconds since the page was loaded. Okay, cool. This is what I was hoping to get to. Once you can, and I think that is what u underscore time is going to deal with, like the time since this was loaded. And then vtext chord must be the position. And just like that, I think we've just learned a whole lot in the space of 15 minutes. Okay, now they're going to talk about uniforms. So far, we've seen how the GPU manages large numbers of parallel threads. Yes. Because of the architecture of the graphics card, those inputs are going to be equal or uniform to all the threads and necessarily set as read-only. In other words, each thread receives the same data which it can read, but it cannot change. And these inputs are called uniform. There is the source of the name of the type there. They come in one of the supported types: float, vec2, vec3, vec4, mat2, mat3, mat4, sampler 2D, and sampler cube. Wow. Okay, so uniforms are defined with the following, with the corresponding type at the top of the shader right after assigning the default floating point precision. Precision medium P float. Okay. You've got your uniform vec2 of u underscore resolution, which is the canvas size. You've got u underscore mouse, which is the mouse position. Okay, so again, in iOS, we don't have a mouse position. So I guess this doesn't apply. But u underscore time, we did see that. The time in seconds since the load. In fact, I don't know how easy it would be to do this. Let's throw you over here. I'm going to bring this guy back here. And what was it? Command 0. There we go. So there's u underscore time right there. Resolution, I don't see this in here, but that's the canvas size. I mean, maybe it might be useful to us. You can picture the uniforms like little bridges between this GPU and the CPU. Okay. The names will vary from implementation, but in this series, I'm always passing u underscore time, resolution, and u mouse. For example, shadertoy.com. Ooh, what's this? What shadertoy.com? Oh. I knew you were lurking somewhere. I'm going to put you over here. All right. Shadertoy.com uses the same uniforms, but with the following names. What's shadertoy.com? Build and share your best shaders with the world and get inspired. Ooh, look at this. Warning. What is this warning? This shader takes too long to compile. A preview image is shown instead to improve browsing. Click on the shader to see it in real time. Oh man, I think my my Intel MacBook would be so upset. Oh my gosh, look at this, you guys. This shows you the time elapsed since load, which I guess would be, I don't see U_time there anywhere. I guess maybe that's iTime. Is that what he says here? Yeah. So in shadertoy.com uses iTime, iMouse, and iResolution, and you see that here. You see iTime, iMouse, iResolution. Converted old plasma. Okay, so I can like move this around. That is cool. And that just goes and goes. Oh, this is awesome. Compiled in 0.2 seconds. So very fast. All right, so this is the kind of stuff that we can expect to make with these tools. Clearly, leaps and bounds over what comes out of the box with SwiftUI. Of course, not really made for this level of control, but it gives us a sprite view, which we can actually use to build in SwiftUI with a sprite view, utilizing these shaders underneath, which is cool. Which means that we can still employ these even in our SwiftUI apps, which is cool. Like I would liken that to well, not liken. I would use that, for example, maybe with a moving background, for example. All right, what do we got? Enough talking. Let's see the uniforms in action. In the following code, we use uTime, which is the number of seconds since the shader started running, together with a sine function to animate the transition of the amount of red in the billboard. So we have uTime, and they've defined it here, but I think we already have it. For example, we don't need to define it in this shader code. It just exists. So U_time we can deal with without defining it here in this file. So void main is GL frag color equals vec4 of the absolute value of the sine of uTime, and then 0, 0, 1. So what did that do? Oh, that's kind of neat. Okay, so we can tinker with that. What this is saying is it's doing the sine of time, which again it's a repeating sinusoid. The value of that is between plus and minus 1. But it's the absolute value of that, so it's always going to be between 0 and 1, which means that your red value is going to constantly be changing from 0 to 1, and everything else is 0. This is 1, which means it's always going to go from black to red. That's cool how it kind of shows us what's going on there. Very cool. As you can see, GLSL has more surprises. The GPU's hardware accelerated angle, trigonometric, and exponential functions, sine, cosine, tangent, asine, arc, cosine, arc, tangent, power, exponent, log, skirt, absine. Okay, so a lot of stuff. Now it's time to begin to play with the above code. Slow down the frequency until the color change becomes almost imperceptible. Okay. So how are we going to do that? Slow down the frequency, which means we're going to, divide it by 100? Uh-oh. Wrong operand types. No operation exists that takes the left-hand operand of type uniform medium P float and a right operand of type const int. Oh, if I do .0, is that acceptable? Well, looky here. That looks like it's imperceptible to me. What if I go divided by 10? Okay, now I'm starting to see a very slow transition. Very nice. What if I were to speed it up until you're seeing a single color without flickering? Okay, so I'm going to multiply it by 2. Looks like I don't even need like a 0. I can just say 2 dot and it understands that it's a float. If I go 3, that's going super fast. Let's go 10. Oh, we're going to get our strobe effect. Let's go 100. Oh boy. 1,000. Okay, that's not until you sing a single color without flickering. Well, there's a single color. It's black. What if I do 1e to the 6? Invalid number. Can I do 1 capital E6? No. Gonna have to be just... I think I broke it. I thought I was supposed to see red, but apparently not. Okay, that's fine. Play with the 3 channels in different frequencies to get interesting patterns and behaviors. Oh, so I can do this. I can be like, hey, I'm going to take this, and instead of 0, I'm also going to do... Wait, does it work for multi-line? I think it does. Oh, this is perfect. Okay, perfect. Okay, so now I can do absolute of this. So now it's turning from yellow to green. Maybe... what if I did... So I'm multiplying it by a value, but what if I added... Or what if I did this? What if I said divided by 2? So this is going orange, yellow, green to black. Okay, so we're having some fun here. So we're essentially just making all sorts of crazy things happening. So we got a patterns of colors changing. That's fun. And just like that, we've just written a shader that changes colors. We could even try doing something random, right? Maybe would that be a good idea though? Because if this function is being called 60 times a second, and you're going to get a random color every time, that might get a little crazy, yeah? Can we use the random? Can we say float R equals rand? Was it S rand? No, rand. I don't think that's it. Maybe they'll gosh. There might be a different value for that. Random. Maybe not. Okay. Milk before meat. All right, that's fine. That's fine. That's fine. I mean, it's almost like we could create our own random red equal to like maybe U times or maybe we can take like a gosh. We could do something weird like exponent of U time divided by 1, 3, 4, 5, 6, 8 point. And then we could say, okay, random red, you're going to be absolute value of the sign of that. And then maybe we'll do that divided by 2. Maybe we'll do that times 3. Okay, I seem to kill it. Never mind. All right. Let's go to the next example. What do we got here? We got GL frag chord. And again, for those of you who are just tuning in, I'm learning all about shaders today. So thebookofshaders.com, just kind of going through this example. My goal for this is to get a little bit of experience with shader code so that I can make my own. I have an idea for what I want to do, and which is to emulate some video game effects that I've been watching and enjoying. Just trying to see how that works. So far, we're understanding how to make uniform color changes all across the board here. But now this one is going to give us something more. This is going to actually give us a pixel dependent value. Vec4 GL frag color also gives us a default input frag chord, which I guess in Swift, the shader language is going to be v text chord. So GL frag chord is maybe the same as v text chord. Should we find out if this is actually true? Like, what if we do this? What if we make a change here and then we press stop? Oh, we press stop and then we try playing this again. Let's see what that does. If GL frag chord is the exact same as v text chord, we should be able to see the effect of the shader. And it turns out that no, it is not the same. In fact, it broke our shader. So lesson learned, we don't want GL frag chord, we want v text chord instead. Okay, well, we had to try. We had to do it for science. So let's just see what they have to say about this, and understanding that this is working for our browser, but that we might have an equivalent in our Swift code here. It's not really Swift code, but you know what I'm saying. So holding the screen coordinates of the pixel or the screen fragment that the active thread is working on. That is what vtext chord is. What they're doing here is they're saying, hey, vec2 of st is equal to glfragchord.xy divided by u resolution. In this case, we don't call it uniform because it'll be different from thread to thread. Instead, GL frag chord is called a varying. Okay. In the above code, we normalize the coordinate of the fragment by dividing it by the total resolution of the billboard. By doing this, the values will go between 0 and 1, which makes it easy to map the X and Y values to the red and green channel. So if we look in here, we have now a vec2, which is, again, that's the same as this guy over here, our vec chord. Same thing. GL frag color equals vec4 of st.x, st.y, 0, and 1. So our red and our green are going to be, now where does it start though? So what I'm going to do is I'm going to see if we can hold on a second. I'd like to try applying it to like our current app to see if like it does any changes, which would be fun. The only problem is we define these uniforms, right? U speed, U strength, U frequency. And so this won't do anything, but maybe it'll still, oh, wow. I didn't realize it was doing that. Okay. I'm gonna bring you back over here. I'm still having issues with my overlay, folks. That's okay. Okay, so what I was gonna do is I was just gonna change this and actually just say, it's just that. So I'm going to let's comment out everything and just play with this. So instead of GL frag chord, it's v text chord, v underscore text underscore chord. But that's a vec2, so that's just that. And then divide it. I don't know if U resolution actually makes sense. Let's just see if this actually works. GL frag color equals vec4. Okay, yeah, let's just try it. Let's just build and see if it crashes. right, so shader code. Okay. So it didn't apply anything to our original shape. Is there actually a... Wanted to see if there was any error messages that show up here. Ah, yeah, look at that. Compiler failed to build the request. Error domain, MTL library error domain, use of undeclared identifier U_resolution. So U_resolution is not part of the shader language for Swift. Okay. Okay. Does not exist. So we're gonna have to find something else. Find something else. Also, Max, what are you doing here? So U_resolution doesn't work. V text core does. Maybe we could find in the documentation for SpriteKit for SK uniform. Maybe we can find what all does exist. Let's see if we can find it out. So we go to Window, Developer Documentation. Let's just take a look and see if we can find some references here. So I'm gonna go to SK texture. Okay. Image that can be used to render. Well, I know what I want to do. Let's do U_speed because we know that one exists. Ooh, there's no results. Oh, terribly terrible. Okay. Let's go SpriteKit. Let's see if we can find anything about SK uniform. Okay, maybe there. A container for uniform shader data. The uniform type. We got a lot of deprecated stuff in here now. Oh, that's very interesting. It's uniform type. None, float vector 234, matrix 234, texture. Texture equals 8. Okay. SpriteKit enumerations. Let's go to data types, maybe. Constants. Physics kit minus GL imports. That's not it. Type aliases. SK color. No. Anything else that we could find? Drawing SpriteKit content in a view. What do we have here? We had SK shader attribute. Maybe if I go back to uniform. Hey, Quicks, how you doing? Aw, I saw your profile picture underneath my camera. How you doing? I need to put that in a different spot. It looks like. I'll put you. Let's put you right here. There we go. Oh, my little picture comes up. Yeah, that's fun. Good times. How you doing? How's your week going? I'm just we're playing with shaders today. I don't know if you remember this project from way long ago when we were making waves with these little shapes and just kind of learning how to make our own shaders for fun because it's super duper fun. Okay, so initializers, we got matrix float 234, vector float. I'm not finding anywhere where we have these values here for our shader code. Yeah, shaders are fun. Shaders are fun. But I'm not getting anything in the documentation that tells us what kind of stuff we can play with. Where even would that be defined? Timing mode, attribute type, blend mode, interpolation mode, render order, repeat mode. No, none of these things look like what I want. Ooh, hexagonal flat. You can't get rid of the hexagons. They're a staple in literally everything graphics related. All right. Yeah, we're not going to find it here. So here's the deal, folks. How do we know? Oh, by the way, check out this cool new scene I have, folks. That was this project. I'm gonna go ahead and X out of this one. Where did you go? Okay, Swift Shaders is back here. Let's go back here. So we tried to use U_resolution to follow along with this example here, and Xcode is complaining this doesn't exist. So I don't know what the equivalent is here. U_resolution. I'm guessing that. Yeah, I'm guessing it just doesn't. Vec2 chord, take a copy of the current texture chord so we can modify it. Chord X plus speed, UX. Okay, so in this case, he's changing the X and Y to be a value that's different. And that's why the wave shape is able to do what it does. But for us, all I want to do is have some fun. Let's do this. Let's just take out U_resolution and see if vtext chord is equivalent or is sufficient for what we want to do. Again, we're changing the red value, we're changing the green value, blue is 0, alpha is 1. And let's see what that does. All right. Come on. Come on, come on. All right. Well, there we go. So this works. It completely destroys our shape. There's no shape. That doesn't do anything for us. Doesn't matter. Because it doesn't use that information. It's just taking the pixel positions and it's saying, hey, I'm applying red for all the X's. I'm applying green for all the Y's. And you'll notice, this is interesting. So remember how in Swift UI, 0, 0 starts at the top left, our coordinate system. But in our shader language, 0, 0 starts at the bottom left. That's why it's all black here, because X is 0, Y is 0, which means we have nothing but blackness. And then as we move towards the maximum value, red becomes 1. And that's why you see it all red here in the corner. And then as we move up, green becomes 1. And then as we go 1, 1, it's red and green, which produces... Uh-oh. Oh, I think I just had a panic. I think my computer's about to die. Yeah, I just got a panic, folks. Oh, no. Oh, what happened? It was too much for him. Oh, no. Okay, this is going to take some time. Okay, hold on, I got to restart this machine. It just gave up. It just gave up. OpenGL puts the origin back to where it's supposed to be. Aha. There you go. I always got confused when I started iOS development. And I was like, why are you starting at the upper left? Like, that doesn't make sense. Everything my math classes were teaching me about graphs and everything was like, well, first of all, 0, 0 is always the center, right? When you're drawing graphs in your math class. But like, it would make more sense that 0, 0 would be at the bottom left than at the top left for me. Okay, it's still resetting. Wow, it did not like that. It got very upset. Okay, hold on. I'm logging back in. Wow, that was too much for it, apparently. I was really stressing it out. It says your computer was restarted because of a problem. Let's see what that problem actually was. Yes, it was a panic. Okay. Panic, CPU 10. Possible memory corruption. So we corrupted the memory by running a shader, which, dang, is dangerous. Well, I'll tell you what, that's just dangerous stuff. Let me see if this works again. Okay. Where were we? To go back to Chrome didn't shut down correctly. Yeah, I know. Like, what the heck, man? Okay. Back to where we were at. Go away. Okay. We went all the way down here. We did the frag chord, and we did this thing. We recreated that, and then we died. And now we're back. It says in the above code, we normalize a coordinate. Okay, yes. We don't have too many resources for debugging besides assigning strong colors to variables and trying to make sense of them. You will discover that sometimes coding in GLSL is very similar to putting ships inside bottles. It's equally hard, beautiful, and gratifying. Can you tell where the coordinate 0, 0 is in our canvas? We just found out that 0, 0 is bottom left. What about 1, 0? 0, 1, 0, 5, 0, 5, and 1, 1. Can you figure out how to use U mouse, knowing that the values are in pixels and not normalized values? Can you use it to move colors around? Can you imagine an interesting way of changing this color pattern using U time and U mouse coordinates? Ooh, that would be fun. I wonder if there's input that we could provide on a drag gesture in Sprite Kit. I wonder, that would be really cool if we could affect the color by moving around and placing that as a variable inside. That would be pretty cool. Okay, so now they're talking about running our shaders in the browser. They've got a GLSL viewer is a great way to compile shaders on your Raspberry Pi. Oh, doesn't Bro have a Raspberry Pi, Quicks? I think he was looking to get one, right? Reason the open frame I use it to play shader artwork. Okay. In order to illuminate the experience of coding shaders, I made an online editor called GLSL Editor. It's embedded on the book's live examples. If you prefer to work offline using Sublime Text, you can install this package. Ooh, look at that. Ooh, hey, we've made some of these. Did you just see a gear shape too? Oh man, this is a game changer for me. Definitely. You know, using path commands for drawing lines and curves is definitely sufficient for most of the things that we do in Swift UI. But if we wanted to get crazy with shaders, look at the geometry goodness that we can deal with here. The online editor, thebookofshaders.com, can share your shaders, both embedded and standalone version of an export button where you can use a unique URL. Let's take a look at this. Okay, so if I go editor, the book of shaders, there it is. So here is our, oh, that is cool. Okay, so I can move this around. So this is using the resolution, it's using the mouse, it's using time. It doesn't seem to be, wait, is it? I can't tell whether my mouse position is is making any effects here, but we've got GLFrag chord XY U resolution. Oh, you can't see the shader code where it is right now. Move it back over here. Resolution X over resolution.Y. Oh, it doesn't want to move it. Okay. Vec3 color equals vec3 0 dot. Color equals vec3 stx sty absolute sine of view time. Okay, so yeah, it's got a whole lot of stuff going on here. What does this test thing do? Oh, that's interesting. Cool. Also, it's not secure, so be careful out there, folks. Okay, I'm gonna X out of this. I'm gonna X out of this. Maybe it was this that was causing the issue. But wouldn't it be cool to be able to make stuff like this? All right, back here, and we're gonna go to sharing your code. Okay, cool. You can make snowflakes. You can use it on your favorite framework. You can use it 3.js. Okay, this is JavaScript code in processing. Okay, open frameworks. Okay, in Blender you can create these. Awesome. Of course, if you're using a Unity or other engine, game engine, there's native support for shaders as well, of course. Okay. Now we're gonna be treated to a screenshot of the Karate Kid. Algorithmic drawing. This chapter could be named Mr. Miyagi's fence lesson. Okay, cool. We mapped the normalized position of X and Y to red and green. Yes. But before we go further, we need to start much simpler. How to make one-dimensional functions, okay? It says that the more energy and time that you spend learning and mastering this, the stronger your shader karate will be. Okay, I can believe it, for sure. This is going to be our fence. We're going to visualize the normalized value of the X coordinate in two ways, one with brightness and one by plotting a green line on top. Don't focus too much on the plot function. We will go through it in more detail in a moment. Okay. Resolution, of course, is you're dealing with how many pixels, width and height that are devoted to the drawing space. Your mouse position, which is not applicable to iOS, but maybe if you were doing a Mac OS app, it would. And time, of course, is the time since the image is first loaded. Plot a line on Y using a value between 0 and 1. Okay, so return smooth step. Okay, it says don't worry about the plot function. Okay, we're not going to worry about the plot function. We're just going to take a look at what's happening here. This is ST, which is our vec2, which is the pixel position. And then we're going to say float Y is equal to X. And then we're going to say, hey, we're going to have a color vec3, and that's vec3 of Y. So you're doing a single argument for a vec3. Does that mean that the second and third arguments are automatically 0? In which case, it makes sense that it would be... Oh, okay. Plot a line. Okay. Let's see what they have to say. The vec3 type constructor understands that you want to assign the 3 color channels with the same value. Oh, I see. So if Y is a certain value and you say vec3 of Y, that means it's assigning the R, G, and B values to that single value. That's a nice shorthand. I wonder if our code has something equivalent. Let's check really quick. Do we have something like that? Can we say vec3 test is equal to vec3 of 2? Now, the frustrating thing about this is that we can't do like I guess I can. Oh, there's no quick help for GLFrag color, unfortunately. That's too bad. But I wonder if this will actually work. Let's try it. Let's press play and see if the runtime gets mad at us. So I defined vec3 as just a single number. And I'm going to build this, and it's attaching to Swift shaders. Okay, so this might take a few minutes. So while we're waiting for that, let's go back here and get some goodness here. The code is your fence. It's important to observe and understand it. You will come back over and over to this space between 0 and 1. You will master the art of blending and shaping this line right here, this green line. Okay, our stuff is here, and our shader code is there. Okay, warning, unused variable test. It seemed to be fine. Compilation succeeded. So it was okay with us defining a vec3 with a single argument. So that's good. That's good to know. Okay, that's cool. What else? It says that the one-to-one relationship between X and Y, or the brightness, is known as linear interpolation. Okay, yes. From here, we can use some mathematical functions to shape the line. For example, we can raise X to the power of 5 to make a curved line. Now, why is this... So it's green everywhere except for black and white here, which I'm not quite sure why that works. Vec4 of color and 1, where color is 1 minus my PCT, percent, I'm guessing, with the plot function, times color, plus percent times vec3, 0, 1, 0. Got it. Okay, so this vec3 right here is showing us that it's green. If I were to change this, to red, now we're at 1, virtually 0, 0. So what it's doing is it's saying, hey, if you are close to X equals Y, then you're going to be more or less red. Otherwise, if you are not nearby, then you're going to be essentially just in the gray space. Okay, that makes sense. So that's kind of neat. Okay, so we can raise X to the power of 5 to make a curved line by saying, okay, so I've got my smooth step here minus my smooth step. Okay, so again, we don't have to worry about our plot function, but all we're saying here is our Y value is X to the power of 5. We're raising X to the power of 5 to make a curved line. Okay, so this is an exponential function. Starts out small and then it gets really, really big. And towards the end, it I guess it normalizes to 1, right? Okay, that's cool. Interesting, right? Yeah. On line 22, try different exponents. Okay, let's try different exponents. Let's, oh, can I just do this? So if I bring it higher, then you can see that like it makes the curve sharper. Like it doesn't actually go upwards until towards the end. Whereas if I bring it down, let's make this a little bit. So if it's the power of 1, no matching overloaded found because it has to be a dot, yeah? Okay, so 1, I go 10, 100, and so on. It's virtually, yeah, if you go much higher than 10, then the effect is more or less lost. I like how like lower values make the curve start much smaller or much earlier. If I go 1.5, 1.1, you can see that the bend starts very small and then it can get bigger and bigger and bigger. Okay, that's cool. Neat. That's just the PAL function. Okay, yeah, we get that. I'm having flashbacks to graphing this semester. Holy Roman Empire. Hopefully they're not terrible memories. Good to see you. How you doing tonight? Welcome. Messing with shaders today. And just learning apparently to paint the fence. That's the goal of this chapter. Thebookofshaders.com. You got a 97 last test. Hey, right on. Final in a week. Good for you. It sounds like you're ready. It's awesome, man. What else we got? So the talking about POW is just yeah, it's just the okay, yeah. The value of the first parameter raised to the power of the second. Okay, that's a very that's a math function that's available in virtually every language you're messing with. Now Most of them are accelerated at the level of the hardware, which means if they're used in the right way and with discretion, they will make your code faster. Yeah, we'll see how you do on your final. Okay, yeah. Remind me to ask you in a week how it went. Let's replace the power function like exponent or log and square root. Some of these functions are more interesting than when you play with them using pi. You can see on line 8 that I defined a macro that will replace any use of pi with a value of 3.1415926. Okay, so let's do that. Let's go exponent. I guess we're gonna have to figure out like what exactly those are. Float x, vec2x, vec3x, vec4x. So if I just do vec4, no, not vec4. I just say, if I just say exponent of just st dot x, maybe just st dot x, st dot y. Oh no, it didn't like that. I wonder why it didn't like that. Okay, so I guess exponent didn't work. What about log? Log, float x, vec2x. Okay, if I just do log, what if I do log? Log. No matching overloaded function found. Oh, why? Well, I guess we'll never know. Let's try square root. Okay, let's do square root of st.x. Okay, square root works. Okay. Now square root of y. Interesting. So you're just gonna see it all the way up here, which is kind of, yeah, it is kind of weird. Okay, so now that we've done square root, now let's try exponent. It's still not gonna work. That's too bad. What about you, log? Log is not having it. Log stx times 3 point. Ah, there we go. So we had to kind of massage this a little bit. And now we've got this log function going on. Okay, well, regardless. Okay. It's basically teaching us how to draw curves. Normally, if you're using, like, for example, the path or CG path, you can just say, hey, add line, add curve, add quad curve. But here we're going to have to be a little bit more like nitty gritty with, we're going to have to actually make some math stuff to draw our curves. I'm sure there's probably libraries that come with the shaders that can actually give us these curves and these lines easier. And maybe we can start building that. Okay. Step and smooth step. Receives two parameters. The first one is a limit or threshold, while the second one is a value that we want to check or pass. Any value under the limit will return 0, while everything above the limit will return 1. Okay, so that means that everything on the left side is returning black, and everything on the right side is returning white. So we have GL frag chord xy over u resolution. Float y is equal to step function of 0.5 will return 0 unless the value is over 0.5. In this case, it will return 1. So this is the value that you need to use. And then this is the thing that you're testing against. So if I were to go 0.8, that means that there's more values that are going to not work here. And this is now 1 minus PCT times color plus PCT times vec3, 0, 1, 0. Okay, fine. So I want to make the threshold lower, then everything below 0.2 is going to be black. Everything above 0.2 is going to be white. Okay, that's cool. That's the step function. So we're dealing with curves. As a function of x, we're dealing with step functions. And you know what? We could probably do like a series of these. We could like add them together to create like maybe like a hatching. Remember we were doing hatching last week? Let's actually mess with that. Let's see if this actually works. Plus step 0.4 st.x. Okay, what did that do? So I had a 0.2, and then I also had a 0.4. And then it just stopped after 0.4. Okay, maybe I'm not doing this correctly. Maybe I have to actually do this inside this color assignment. But when I tried to do use multiple steps, that kind of killed this. It wouldn't let us go to the end. Can I move this? No, I can't. Okay. All right. They're like, hey, paint the fence, man. Don't try to go advanced. You got to learn this one step at a time. That's one of the things that I have a difficulty with, is to like not like want to like step outside the tutorial and just like kind of like try to figure it out on my own. Okay, what's this other function? This is known as smooth step. First of all, smooth step, I mean, so it says that GLSL has some unique native interpolation functions that are hardware accelerated. Do we have an equivalent in iOS? Can we use smooth step? Let's find out. Because we were doing this and this was working just fine. But now I'd like to know if we can actually do this, because wouldn't that be cool to be able to like use this out of the box? So I'm just going to take this, do that. And then in my main, I'm going to say, okay, ST is a vertex, and then I'm going to do this. And then I'm going to do this. And let's see if this actually works. So color equals vec3y. We're going to get rid of this because that didn't work. Looks like everything needs semicolons as well. That's one thing that we haven't had to worry about in Swift. But we do have to have semicolons in this. So let's see if it understands what smooth step is. I'm going to go ahead and press play and see if it actually builds. And no, unfortunately, smooth step does not work. Error, use of undeclared identifier ST. Oh, wait. Oh, is that my bad? Oh, shoot. I forgot to define this. Oh, that, okay. Okay, hold on. Vec2 ST is equal to vtex chords. I think that's what it was. Vtex chord. Vtex chord. Okay. So press stop and let's press play again. See if this actually does something. Hey, look at that. We get smooth step. So smooth step works for our Swift code. Very nice. There it is. Okay. Very cool. And I'm guessing that I'm guessing, oh, smooth step is already here. Why did the step interpolation receives two parameters. Oh, we do step here. Okay, so yeah, so step works and smooth step works as well. Cool. Cool. So we did the smooth step. This one will, given a range of two numbers and value, this function will interpolate the value between the defined range. The first two parameters are for the beginning and the end of the transition. The third is for the value to interpolate. So this is how we get this this nice S curve in the middle here. So if I say, hey, I want to go between 0.3 and 0.6, then I'm gonna get that going on. If I go between 0.1 and 0.8, then yeah, it does this nice little curve here. So this could be equivalent to the OG curves that we made in our shapes library when we're dealing with you know, those architecture curves. I need a smooth step now. Very cool. Oh, now for the cool stuff. Look at this. Okay, so we got sine and cosine. When you want to use some math to animate, shape, or blend values, there's nothing better than being friends with sine and cosine. There is, oh, MacGyver's Swift Army Knife. Apparently these are quite useful tools in the shader community. This is what sine and cosine look like. The fact that they return normalized values in such a smooth way makes them an incredible tool. Ah, okay. While it's difficult to describe all the relationships between trigonometric functions and circles, this animation, yes, that's great. Take a look at the sine wave. Okay, yeah. Okay, try the following exercises and notice what happens. Add time to x before computing the sine and internalize that motion along x, which is fine because, again, u underscore time is constantly increasing as soon as the view loads. And if you take the sine of that, you're going to be constantly getting this value between 1 and -1. Multiply x by pi before computing the sine. Notice how the two phases shrink. So each cycle repeats every 2 integers. So now, okay, is this, wait a second. So, add time, u time to x before computing the sine. So I just do this, u time. Oh, okay, perfect. Okay, so this is showing us in real time what's happening here. Okay, multiply x by pi. Let's go pi times. Okay, the two phases shrink. So so here you got one cycle. Here you've got pi cycles. Okay, if we do 2 times pi times x. Oh, do I need a dot? I need a dot. Okay, cool. Now you've got, okay, so that's fun. Multiply time by x before computing the sine. So yeah, the frequency between the phases becomes more and more compressed. Okay, so yeah, so we can multiply u time times x. Oh, what? Oh, that looks so cool. Okay, so if I get rid of the 2 pi x, oh, it's still okay. So it's getting more and more. Now that is something. Look at that. Look how noisy it is. And it just keeps on building, and it's kind of scrunching itself together. Note that U time may have already become very large, making the graph hard to read. Oh, I see. So if we refresh this page and we go all the way down here, okay, because U time is always increasing. So if I say X times U time, okay, so this is where it starts. Okay, so that's what was going on. This U underscore time continues to increase forever. And so when you're in a browser, this is what's going on. It's constantly compressing, so that's fun. I'm gonna bookmark this particular page because holy crap. Let's choose another folder. Let's make something called let's go new folder and shaders. Throw that into there. So this is our Paint the Fence web page. If you want to mess with shaders in one dimension, you want to see what happens there, then this is a perfect opportunity. Okay. If you add 1 to this, oh, maybe it's after the sign? +1 dot. Okay, yeah, that makes sense. So the y value, of course, is the sine of the x +1. So you're shifting everything up by 1. That's fine. Multiply sine x by 2. See how the amplitude doubles in size. Yeah, that's easy. That's just your standard a times a. Yeah, so that's multiply by 2. And yeah, this is getting kind of crazy. So I'm just going to do that. Okay. Compute the absolute value of sine x. It looks like the trace of a bouncing ball. We know that. Again, this is just absolute value of sine x. Oh, let's not do the 2 times. And let's do that. Boom. That stays always a positive value. Yep. Okay. So again, yeah, flashbacks to graphing class. Extract just the fraction part of the resultant of sine x. The fraction part. What is this? Oh, this is making our sawtooth wave. Okay, that's cool. Cool. Go all the way back down here. Some extra useful functions. To get digital wave of 1 and -1 values. Digital wave. Add the higher integer and smaller. Okay. At the end of the last exercise, we introduced some new functions. I'm just going to skip this part. This last part. Now it's time to experiment with each one by uncommenting the lines below one at a time. Get to know these functions, study how they behave. Why? A quick Google search on generative art will tell you. Keep in mind that these functions are our fence. We are mastering the movement in one dimension up and down. Soon it'll be time for 2, 3, and 4 dimensions. Okay, so if we return only the fraction, so do this. Do the ceiling, the floor, extract the sign. So it goes from negative to positive. So, okay. Return the absolute value. Yes. Clamping. From 0, constrain X to lie between 0 and 1. What if I change this to 2? Okay. Let's go between -1. Okay, cool. That's what the clamp function does. Neat. Return the lesser of X. And okay, so the min max. Okay, those are fine. Okay, cool. Great. Advanced shaping functions. Oh, okay. So if you're a fan of the Bezier curves, this is a way to get to what we were doing in the Swift UI realm. Is this all building up to an OpenGL Rouleau triangle, KNH? I think you are right on the money there. Absolutely. We need an OpenGL Rouleau triangle that can rotate and transform and scale and all those things in real time in a pattern, and that would just be the best. Yeah, I think that's what we're leading up to for sure. This cool stuff, and it looks like a lot of these functions are available in our shading language here, so should be a pretty. Wait, can I mess with this? Okay, these are just PNGs. Okay. Golan 11 is great documentation of more complex shaping functions. Porting them to GLSL is a really smart move to start building your own resources of snippets of code. Hey, we're making libraries. If we want to make our own Bezier, this is a cubic Bezier through 2 points. So we can make some customized curves, which would be really great. Because you can only go so far with your quadratic curve and your regular curve, right? But if we could make even more fundamental curves in our toolbox, that could really open up some opportunities here. Let's just see what this what he has to say here. So it's shapers. Let's go to this link, flong.com. I thought I opened the link. Okay. flong.com/archive/text/code/shapers_poly. Okay, I wonder. Okay, what does this say? Your connection to this site is not secure. Okay, so don't put any credit card information into this site because you might get got. All right, what does he have to say here? Polynomial shaping functions. Oh, wow, look at all of this. Double cubic seat. This would be a useful approximation for cosine and sine trig functions for a small microprocessor, such as an Arduino. Oh, I see. So what he's pointing out here is saying, like, on some systems, like, calculating the cosine and the sine of something can be really computationally expensive. You can get a really good approximation from something like this. 4/9 x to the 6 minus 17/9 x to the 4th and so on. that'll give you a pretty good approximation for the cosine. So that's kind of a cool thing to have. We probably don't need it for mobile development, but it could be useful on other platforms. Okay, so this is a great resource. Double cubic seat with linear blend, double odd polynomial seat, symmetric double polynomial sigmoids. Okay, quadratic through a given point. This is cool because you know how like we've been making quadratic curves where we like have to kind of like guess like where our control point's going to be. Like when we say okay, I want to make add curve to a point with a control point of somewhere over here. But if we wanted to actually control where that line was passing through, you can do it this way, knowing that your start's going to be 0, 0, your end's going to be 1, 1. Then you can be like, hey, I want a curve that passes through this point, and you can control that. That is very cool. It's a great resource right there. And he's got, this is basically like a cookbook, a recipe. This is what that is. And your inputs are going to be what? Epsilon. Okay, a equals 0. These are all. They're 1 minus 1 plus 1. Say A is max param A, max param B. Those are all the same. Float X, A, and B. Okay, so X, A, and B are the inputs. What does A and B refer to? But A was already here, so why is A being redefined right here? I don't know. Oh, A equals the minimum of the max parameter of A and the max of the min of A and A. Okay, so some sort of normalization is happening here, where basically what he's doing is he's sanitizing his inputs for A and B, constraining them to be whatever's going on here, and then saying, okay, then your capital A, your capital B, Y goes min, 1 max, return Y, and that function you can use to create some value there. Okay, so we are definitely starring this as well. Again, I'm thebookofshaders.com is where we're starting from here. I'll go ahead and I'll copy and paste this link though, so you guys can see what's going on here. So that's for polynomial shapes. This is for exponential shapes. This is for circular and elliptical shapes. Okay, let's look at that one. I like that. I like the sound of that. Okay, while it's loading, let's just keep on moving. Like chefs that collect spices and exotic ingredients, digital artists and creative coders have a particular love of working on their own shaping functions. I mean, yeah, I feel that. We've been messing around with our shapes, of course, but these are like reusable functions that we can use as building blocks inside, like say our path types, or shapes that use path in rectangle. We have created a few, like for example, let's take a look back at our shapes library. So we have made a few, what can I say here? What have we done? For example, we've made, are you here? Path extensions. So a little over a year ago, we made something called the OG type. With adding S curves, and this looks like it's a mutating function on path, where we're doing a move to, we're doing 2 quad curves and scaling. So this is kind of like our own toolbox, yeah. But we can do something similar with our shader. And this Swift library is only dealing with Swift UI code. It's not dealing with shader code. But we could have an equivalent shader library. But I'm no expert on this yet. So I'm going to need some time and practice to make some stuff that could be useful. This is an impulse function. That's cool. This is a bunch of a parabola. So if we wanted to make like gradients, for example, here is like basically a linear gradient of going from black to white and back to black using the parabola function. I wonder if we could possibly generate our own gradients using something like this. Well, it looks like we can. Oh wow, look at that. That is cool. Very cool. And then wait, there's a play button. Oh my gosh. That is mesmerizing. That's awesome. In the next chapter, we're going to start using our new moves. First with mixing colors and then drawing shapes. Okay. Take a look at the following table of equations made by Kind to see how he is combining functions and their properties to control the values between 0 and 1. Now it's time for you to practice by replicating these functions. Remember, the more you practice, the better your karate will be. Here are some tools that make it easier for you to visualize it. If you have a Mac OS computer, type Grapher in your Spotlight, and you'll be able to use the super handy tool. Wait a minute. Grapher? Holy crap. I didn't know we had this. Eh? Oh, I can't. I can move, but I can't make it bigger. Okay. Margins. Bro. Did you know about this? Did you know about this? That is so cool. Oh man. What can I do with this? Can I So here are some templates, but can I okay, I've got 3D graphs. Oh, frame, gradient, flat, cylindrical system. Oh my gosh. Okay, we'll choose that. And now what? Windows doesn't have this. This has been in Mac OS 10 for quite a while. KNH, I had no idea this is like a hidden gem. Why didn't you tell me about this? Just kidding. Wow. Okay, so Z, what do I do? Just type in numbers? 3 times X? What? Dude. Oh man, I could play with this all day. Oh geez. That is dope. So you can like create like multiple. If I press the plus button, new equation from template. Oh wow. Okay, so I can make a curve. Let's make a cylindrical curve. Oh my gosh. One. Enter. Oh my gosh. Okay, well that's fun. Graph toy. Once again, made a tool to visualize GLSL functions in WebGL. This is another link, so let's take a look at that. Dude. Okay, so Roman Empire, if you just use a browser, you can play with this, looks like. A bunch of functions here. Jeez. Okay. Basically a signal generator. That's awesome. Shader Shop. This amazing tool is created by Toby Shoshman. Will teach you how to construct complex functions in a credible, visual, and intuitive way. All right, let's take a look at this. Shader Shop. You can make harmonics. Okay. You can make noise. You can make. Oh man. Excellent resources here. I'm gonna highlight all of these guys. It's freaking amazing, dude. That's so cool. All right. What's next? I had no idea. I've just opened Pandora's box. I'm gonna be having a lot of fun with this. All right. We haven't had much of a chance to talk about vector types. I mean, we kind of do because we know that vec2, vec3, vec4 just means we've got like multiple. Vec4 is RGBA, vec3 could just be XYZ, vec2 is XY, and so on. If you're familiar with object-oriented programming, you probably noticed that we've been accessing the data inside the vectors like any regular C-like struct, so like red.x.y.z, for example. Defining color using X, Y, and Z can be confusing, sure. That's why there are other ways to access the same information but different names. The value of X, Y, and Z can also be called R, G, and B, and S, T, and P, which are usually used for spatial coordinates of a texture. So you can say vec4, you can say vector R is equal to vector X is equal to vector S. RGBA is equal to XYZW is equal to STPQ. Okay, that's actually helpful. These are different ways or just nomenclatures designed to help you write clear code. The flexibility embedded in shading language is a door for you to start thinking interchangeably about color and space coordinates. You can combine these in any order you want. So you can say yellow.rg. So red green is equal to vec2 What? So you can so this is like shorthand. You can say you've got a vec3 called yellow, and if you want your red and green channels to be equal to 1, you just say yellow.rg. Can we do that in here? Let's try this. I want to see if this translates. I'm sure it does. We got to go back to, okay, so we're doing the smooth step. What are we going to do here? Let's just say, okay, we're going to say vec3 color. Vec4, okay, so vec3 color equals, okay, vec3 color. And I'm going to say color.rg is equal to vec2 1.0. So what this should do is give us red and green to make yellow. Do we have to assign assign 0? This is called swizzling in GLSL. Okay. Making magenta, yellow.rbg. Assign the channels with green and blue swapped. Wait, what? So instead of RGB, it's RBG. So you're switching. So now it's 101 for magenta. And then for green, you're saying blue, green, blue. Oh my gosh, my golly. What have I stumbled upon? There it is. There's the yellow. Wow, that is cool. Oh man. Crash course in shader fundamentals. So we can do that with the shorthand stuff. That's quite clever. Okay, so now that you know how colors are defined, it's time to integrate this with our previous knowledge. There's a very useful function called mix that lets you mix two values in percentages. Can you guess what the percentage range is? Yes, it's between 0 and 1, which is perfect for you after these long hours practicing your karate moves at the fence. Let's just click on what mix is. Oh, it's got a... Oh, this is awesome. If you click on that and you do a search, it already has an example for you. For example, we've got color A and color B, and we're saying percentage is equal to absolute value of the sine of u time. This is traveling between 1 and 0. And it mixes between color and color B with the value between 0 and 1 to mix the two colors as a function of time. Oh, gosh. So green for the first one. And then we'll go like blue for the second one. And then, yeah, it just toggles between green and blue using the mix function. And the thing that changes is PCT, percent. That's the one that's changing as a function of time. These are constants. So it's just swapping back and forth like this. And wow. This is using smooth steps again with the plot. Mixing color A and B with a percentage, which is a function of X. So now you're going between blue and yellow. And that's what gives you your linear gradient with the mix. Jeez. This is so cool. Okay, let's go back. What did they have here? Oh, so this is just telling us exactly what we just kind of stumbled upon when we clicked on that link. Mixing color A and B. Make an expressive transition between colors. Think of a particular emotion. What color seems most representative? How does it appear? How does it fade away? Change the beginning and ending color, then animate the transition using shaping functions. Robert Penner developed a series of popular shaping functions for computer animation known as easing functions. We've dealt with this before. The ease in, the ease out, the ease in out. And I believe that the only ones that are natively supported, or at least have been defined, at least with the animations that we use in SwiftUI, are the ease in sign functions. But take a look at these other ones that we have. We've got quad values. We've got exponent. We've got ease in back. What the heck is this? This is like kind of like going backwards. We've got ease in bouncing. I guess that could be similar to the spring animations that we have, but look at all this. Wow, this is another awesome resource. Holy crap, you guys. I'm learning so much today. I click on ease out sign. This function. So this is showing us CSS using easing gradients. Man, this is a gold mine, you guys. This is awesome. Whoops. This is in the way. Move you back over here. All right. So if we go sizes, okay, so that shows like the animations that happen. Okay, fun. That's a great resource. Okay. So the easing functions were developed by this guy, Robert Penner. Let's see if we got Wikipedia on this guy. There he is. He's in LA. American mathematician whose work in geometry and combinatorics has found applications in high energy physics and more recently in theoretical biology. We have him to thank for these easing functions. That is pretty cool. That is very cool. Good job, Robert. We are hooking the transition to normalized x coordinate and visualizing with the line. Right now, all the channels go along the same line. Uncomment 25 and see what happens. Oh. Then try uncommenting lines 26 and 27. Remember that the lines visualize the amount of color A and color B to mix per channel. Okay. So when we started out here, it was just linear from blue to yellow. And then when we made the R a smooth step, then we saw that we crept in a little bit of orange there, and then we went green. You can see that happening. And now you can see with the blue, even more of a gradient. So now we get like the full rainbow spectrum here. And all we did was we changed the percent, which is a vec3, as a function of x. We did a smooth step here, we did a sine here, we did a pow here. Okay. Wow, that's very powerful. That's cool. You probably recognize the 3 shaping functions that we're using on lines 25 to 27. Yes. Play with them. Play with them. It's time for you to explore. Show off your skills from the previous chapter. Make interesting gradients. This is all about making gradients, which if you think about in SwiftUI, we have radial gradient, we have elliptical, we have linear, angular. But now we could, by following this, we could probably, it might take a few steps, but what we could do is we could create an image, like a SwiftUI image, based on a shader. So we could say, okay, so we got like a sprite view with a shader with our shader code, generate an image from that, convert it to a SwiftUI image, and make that like the foreground style for some shape. For example, we could do that. So now we're working from the opposite back to what we would want to do here. So we could have like a whole like library full of like different types of gradients. That would be kind of interesting and perhaps useful. Compose a gradient that resembles a William Turner sunset. That is one of the exercises for this chapter. Okay. Animate a transition between a sunrise and a sunset using U time. This is like, okay, so this just jumped up in difficulty, like right away. Can you make a rainbow using what we learned so far? Well, we just did. So there it is. Oh, but like a rainbow is in like a rainbow shape. Yeah, I guess we could do that. Use the step function to create a colorful flag. I'm not going to go through these exercises right now. I'm just going to keep on reading. I'm just thinking about applications that we could use in our SwiftUI projects. Utilizing these different shaders, which again, my goal is to have something that's interactive. So like if we could use a drag gesture, for example, to be the input for the shader and have it change dynamically. This could also help us with like animations, because like, for example, like I'm thinking like along the lines of like Alan Wake fog, where we could maybe create like a noise function that moves in time, or on a drag gesture we could get like fog to move, like smoke to move. That'd be pretty fun. possibilities are endless. Okay, let's take a look at what HSB is. We can't talk about color without speaking about color space. As you probably know, there are different ways to organize color besides by red, green, and blue channels. HSB is hue, saturation, and brightness, or value, and is more intuitive and useful organization. It's more intuitive, is that right? Take a moment to read the RGB H2SV and HSV to RGB functions in the following code. By mapping the position on the x-axis to the hue and the position on the y-axis to the brightness, we obtain a nice spectrum of visible colors. This spatial distribution can be very handy. It's more intuitive to pick a color with HSB than it is with RGB. Okay. Okay, so there's the code from RGB to HSB. So it's this value K, which is a VEC4, which is 0, negative 1/3, and 2/3 and negative 1. Okay. We mix. Oh gosh, this is. Oh wow. I'm not even going to pretend to know what's going on. We're mixing the blue and green of C, which is this incoming, with this K is WZ, which again, what was it? It's XYZW. Yes, exactly. Anonymous. Thank you. So yeah, I'm just gonna take this for granted. That's what's happening. How you're converting your RGB to this new thing. Well played. HSB to RGB. Okay, so you can convert one to the other. And then wow, so that's how we deal with that. And then it talks about polar coordinates. So based on your angle, and this is how you get like these angular gradients, which is what we've seen. And this is a cool angular gradient because you've almost got this like pedal effect. Like you can see like you can see this happening. I'm not sure why that was marked anonymous. Was that you, Cocotype? Thank you. How you doing tonight? That's funny. This is really cool. So we're making these like these very interesting angular gradients with you've got some sort of fuzziness happening here as well. Jeez. Dude, this is like the shader Bible, man. Just got back from losing at pub trivia. Was there a prize for the winner? Or was it just notoriety among your peers? I tell you, like, whenever I play a trivia game for like high stakes, my mind just goes and like I forget everything I've ever learned in my life. Just money. Try the following exercise. Modify the polar example to get a spinning color wheel, just like the waiting mouse icon. These are great exercises, man. This almost seems like it could be like a school subject. Like taking a course on shaders. Is there such a thing? So like when I was in school, there was no like game development course, right? There was no, I mean, there were CS courses, but I didn't know of any, like, maybe they existed, but this seems like this would be straight out of a textbook. This would be really cool. Use a shaping function together with the conversion function from HSB to RGB to expand a particular hue value and shrink the rest. So you get something like this. Using the solar spectrum. Okay, so you could like create these functions that are weighted and have like a tail end here with the blue. That's cool. If you look closely at the color wheel used on color pickers, they use a different spectrum according to red, yellow, blue color space. For example, the opposite color of red should be green, but in our example, it's cyan. Can you find a way to fix that in order to look exactly like the following image? Exactly like the following. This is a great moment to use shaping functions. Oh man, I bet like I could just spend so much time here like hitting my head against a wall trying to get these. But it seems like this is the kind of stuff that they're hoping you do, is just kind of like practice this so that you can eventually like create some like spectacular results. Read Yosef Alber's book Interaction of Color. All right, got another link here. Conceived as a handbook and teaching aid for artists, instructors, and students, this timeless book presents Albers' unique ideas of color experimentation in a way that is valuable. All right. Oh, wow. If I just mouse over this. Oh, if I clicked on that, then it takes me to this interactive editor. Okay. To begin the study of how color deceives and how to make use of this, the first exercise is to make one and the same color look different. Okay. Again, this is like we've just opened up a whole new world with this. Note about functions and arguments. Before jumping to the next chapter, let's stop and rewind. Go back and take a look at the functions in the previous examples. You notice that in before the type of the arguments. This is a qualifier. And in this case, it specifies that the variable is read-only. In future examples, we will see that it is also possible to define arguments as out or in-out. Now, we've seen the in-out attribute in our Swift code, which means that you're passing a value by reference, which means that you can, and actually this, you can see this in the path initializer. If we go to, where are you at? Developer. Oh, there you are. If we go to developer documentation and we go to our path initializer, give it a moment. Hello. Oh, I want you. Yes, there it is. The in-out means that when we use our path initializer in where is it? Path in. This closure, this is an in-out variable because the very thing that we're defining, we're providing a reference to itself. And so you can do that as well in shader code is what that looks like. So we could probably do something with this. Could have some method, like something, which is like an in-out. Oh yeah, look at you can already see in-out float x, and we'll just say x equals x times 3 for some reason. I don't know. And then we'll say we'll just say well, yeah, I don't have to worry about it, but that capability exists. Fun. Okay. There's also in for read only, there's out for write only, and in out for read write. In is the default, I suppose, so you don't have to really qualify those. Out is write only. The last one is conceptually similar to passing an argument by reference. Yeah. You may not believe it, but now we have all the elements to make cool drawings. In the next chapter, we'll learn how to combine all our tricks to make geometric forms by blending this space. This is what I want. This is what I want. Shapes. Shapes. Finally, we've been building skills for this moment. You've learned most of the GLSL foundations, types, and functions. Not really, though, because I just kind of glossed over the fundamentals. Didn't really paint the fence, but you know. It says, you have practiced your shaping equations over and over. Now is the time to put it all together. You are up for this challenge. In this chapter, you'll learn how to draw simple shapes in a parallel, procedural way. This is what I came for. This is what I want. Okay. Imagine we have grid paper, and our homework is to draw a square. What do? You'd paint everything except the first and last rows and the first and last columns, right? How does this relate to shaders? Because each little square of our grid paper is a thread, a pixel. Each little square knows its position, like the coordinates of a chessboard. We used to map X and Y to the red and green color channels, and we learned how to use the narrow two-dimensional territory between 0 and 1. How can we use this to draw a centered square in the middle of our billboard? What are you picking up GLSL for? For fun. No, there's some game UI elements that I can't quite replicate using like your standard Swift UI animations and shapes. And so I want to be able to like add that as like a background using a sprite view. So it technically is still Swift UI, but using Sprite Kit. And we can build our own shaders to kind of recreate those effects. So yeah, I guess it's like the next level in dealing with Swift UI graphics, I guess. So that is my goal to get a little bit more knowledge with this side of things. For example, I've been wanting to make some cool effects, like animated effects, like for example our Alan Wake project, which I don't have a whole lot of time left for tonight. I was gonna play a little bit, but I don't know if I'm just having too much fun with this right now. Where'd you go? You recall the title or the chapter screen, or I guess it's like the end of episode animation where like the title comes up and he's like shining his flashlight around, and you've got like the Alan Wake lettering. Which we currently have a placeholder that looks kind of bad. It's this guy with the mirrored text that isn't quite mirrored yet. I want to create a smoke effect. I don't know how to do that in Swift UI proper. Like the only thing that I've been able to kind of do to replicate that is using like a blur on like say like a random image, and just like mess with like the opacity. But I want to be able to animate that, Alanmate that. I want to put smoke in here, and I want it to like move, like based on like a drag gesture. I want to create like our own like smoke effect. That's why. And yeah, there's a lot of work that needs to be done here, but yeah, we're making stuff little by little. It seems like things like this we can also do with shaders, which I feel like I would probably like have some sort of threshold. I was like, okay, like if I can do this with just like your standard draw calls, like your add curve, your add line, add quad curve, we'll do that. And then maybe we'll also add some additional ease functions for drawing curves based on this library, that these being on the shoulders of giants, essentially, to build that out. But yeah, that's the long answer for why I want to do it. So they're about to teach us how to actually draw lines, like shapes. Starting with pseudocode. If X is greater than 1 and Y is greater than 1, paint white, else paint black. Okay. Now, let's replace the if statement with step. Instead of using 10 by 10, let's use normalized values between 0 and 1. So we've got our texture coordinates. We have our color is starts at 0. Each result will return 1 or 0. So left is equal to step of 0.1. Bottom is step 0.1 STY, similar to Y greater than 1. The multiplication of the left and the bottom will be similar to the logical AND. So color equals vec3 left times bottom. So I'm multiplying 2 steps. Now before I was trying this by adding steps, but that wasn't doing anything. But if we multiply them together, then we should be getting something like this. Okay, let's try it. So I'm just going to take this, I'm going to copy this, and I'm going to go back to our Swift shaders. So we're back here in SK water, and we're going to do this. So this has to be vtex chord, and then color is vec300. Left is going to be step 0.1 stx. I'm not sure if these are normalized though. I think vtex chord is just going to be like the actual number. What I need to do is be able to like divide it by the maximum, which is what they were going to do. So this actually might not work out of the box. Let's just see what this looks like. Okay, we're going to build and run. And let's go back to our shader code. Oh, I'm tapping on the whatever. Okay. So we've got this going on, which is an L shape. There's our add lines. A little bit more involved though, yeah? Left and bottom. And that's what it is, the left and the bottom. So could we essentially make our right and top without looking at the code? Let's try it. Okay, float top is equal to step 0.9 st.y. And then we're going to say float right is going to be equal to step 0.9 st.x. And then I'm going to say left times bottom times right times top. Let's see if that gets us our square. Uh-oh. Nope, that didn't do it. That did this instead. So now we have a small unpainted region. That's not what we were looking for. Let me see if I did this wrong. Left is step 0.1 stx, similar to x is greater than 1. Right is step is 9 is greater than 0.9. Same for top. The multiplication of left and bottom will be similar to the logical end. So if I said left times bottom times right times top. So I thought that was going to work for this, but apparently no. Didn't work. Although there could be a scaling issue. I mean, I honestly have no idea if VDEX text chord is even like an or normalized I'd like to think that it was, but I have no way of knowing, I guess. Let's try just doing right times top and seeing if that will show something on the top and on the right side. Let's try that. Because if that works, at least we'll know that that'll probably tell us if we are normalized. Wait a minute. If anything that's greater than 0.9 STY will be white. Wait. Oh, I see. I see what's happening here. This is doing exactly what I'm asking it to do. This is saying anything that is greater than 0.9, you paint white. And that's why you have this little square at the top, because this is 90% in the X direction. Everything is black unless you paint it white. Okay, so this is doing what I'm asking it to do. Whereas anything that's greater than 0.1, you paint white, and that's why with the left and the bottom, okay, I just have to, I couldn't quite figure out what I was going for. The painted region is actually white, which makes sense because you're saying left times bottom is your color, which is a Vec 3, and your frag color is going to be white. Got it. Okay, so I go back to left times bottom. As anything that's bigger than 0.1 in the X direction is going to be painted. Anything that's greater than 0.1 in the Y direction will be painted, which means that we... Oh, because it's bottom, not bot. My mistake. Go back. Go back. Okay. So I was foolishly thinking that the black part was being painted, when in actuality, the part that's getting actually painted is this region, the white region. That's why it makes sense that when I did left times bottom times right times top, that the only thing where that was true for all cases was the 90%, which is why I only saw this part painted. Everything else was not painted. So when you're creating an outline of your shape, it's almost like, well, at least in this particular example, it's like the reverse of what I thought it was going to be. So I wonder if the website's going to tell me, okay, the stuff that you actually want painted, you're going to have to do like either the inverse of that or 1 minus that or whatever. Okay. And yeah, naturally it's telling us that it'll turn every pixel below 0.1 to black and the rest to white. The multiplication between the left and bottom works as a logical AND, where both must be 1 to return 1. This draws two black lines, one on the bottom and one the other on the left side. In the previous code, we repeat the structure for each axis, left and bottom. We can save some lines of code by passing 2 values directly to step instead of 1. That looks like this. Borders is equal to step vec2 of 0.1 comma st. Oh. Okay. Hold up a second. So percent is equal to borders dot x times borders dot y, which was the exact same thing as vec3 of left times the bottom. So you had your left here, which is a step function with a single value. And then you made a vec3. Here, we have a vec2, and then st is also a vec2. So you're doing a step function 0.1 for both x and y, and then you're saying, okay, my percent is equal to borders dot x times borders dot y. So far, we've only done 2 borders. Let's do the other 2, top right. Check out the following code. Bottom left is BL, is step vec2, yes. Percent is BL dot x, BL dot y. And the top right is going to be step vec2, 1 minus. That's what I was missing. So here, when I said it was step of 0.9 st minus y, what I really needed to do is say also 0.1, but 1 minus that. 1 minus that. Then if I did this again, times top times right, maybe that would give me what I'm looking for. There we go. So step functions to give us our, that 0.1 is essentially the width of the line. That, again, in this case, it's actually unpainted. Which is just so weird to me. It's like you're filling the negative space instead of like stroking the lines. So how would that relate to creating diagonal lines? I guess it's that step function that the smooth step, is that what it was? Oh, so what they're doing here is they're they defined a percentage, and then they said percentage times equals this multiplication of TR. And then assign the color, again, like normal to that. I mean, it's kind of the same number of lines. Like I said, left, bottom, top, right. They're saying bottom left, top right. It's the same number of lines of code though. But I wonder if theirs is more flexible. Note that in lines 18 and 22, all the sides are being multiplied together. This is equivalent to writing, yes, what we just did here. BLX, BLY, TRX, TRY, yep. Interesting, right? I think so. This technique is all about using step and multiplication for logical operations and flipping the coordinates. Okay, before going forward, you should need to try to change the size and the proportions of the rectangle. So we can do that by Instead of saying 0.1, we could say like 0.2, and that would just make it thicker lines, right? Experiment with the same code, but using smooth step instead of step. Okay, so again, like if we said this is going to be 0.2, and then 0.2, yeah, you got a thicker line here, which is fine. And then they say experiment with the same code, but using smooth step instead of step. Note that by changing values, you can go from blurred edges to elegant smooth borders. Huh. Okay. So we can add a blur effectively. Do another implementation that uses floor. Choose the implementation you like the most and make a function of it that you can reuse in the future. Make your function flexible and efficient. That's our goal. We're going to be building a toolkit. Make another function that just draws the outline of a rectangle. Isn't that what we just did? Or no. What we did was we drew an inner rectangle. I keep on forgetting that this is flipped. That like the white area is what we're actually drawing. Or what we're actually painting. And to be fair, like if I were to make this like a background color of say like blue, would that then make this? Let's try that. Let's look at our code here. Here is our shader. Personally, I can't stand flexible and efficient functions. Is that right, Cocotype? You prefer inflexible and inefficient functions. Going for that retro low FPS. Where is it? Where would I put this? I need to put it inside. Okay, I gotta press stop. I guess it would be in the shader scene. No, this is gonna be in shader test view, where I would say scene update texture image, and then what? Sprite view scene options allows transparency, ignores sibling color order, frame, and let's see if I gave it a foreground color of, let's just say green, and see what that looks like. So here's my scene, my shader applied, and let's press play. Oh, if I see a green interior, then I'll know what we're actually painting. If you're not spotting, you're not trying. Where'd it go? Oh. Shoot, it didn't work. Oh, what's going on? My sprite view ignored my foreground color. What do you think that means? It means that our sprite view is effectively impervious to color, basically fills. Okay. So this white region we can't fill with green just using our standard foreground color. We're gonna actually have to go inside this sprite view and mess with it. So if we go back into here, well, our scene is our scene. Let's go into, okay, what scene was it? Oh, could it be because, wait, I'm just gonna try one thing here. I'm gonna try turning this into a state object. I don't know if this is what I should be doing. It seems like that's what I should be doing. Oh, just kidding. Shader scene. Are you not an observable? You're an SK scene. Oh, okay. But so even though I'm a reference type, even though I'm a class, I have to specify observable object in order for it to for sprite, sorry, for state object to do its thing. I don't know if this is actually doing anything because I haven't declared any published properties. I've only got a shader and node, which I don't know. It succeeded. All right, let's see. Let's see if turning it into a state object did anything. I don't think it will. Yeah, there's nothing there. Okay, so what we need to do is we need to go back here. We're going to take a look at our shader. We say our node shader equals new shader. But what does an SK shader allow? The shader itself is the painter, right? So does it even translate to be able to multiply a shader's result or its viewport or whatever it's called by some sort of a foreground color, or is that just like apples and oranges? Let's take a look at what SK shader actually does. It's an NS object. It has a source. It has a set of uniforms or an array of uniforms. It has attributes. SK attribute, name and type, float value. Okay. So clearly, it's not a user-friendly API in the sense that there's really not much you can do. Let's take a look at this. It's very very small font size. It holds a custom OpenGL ES fragment shader. Shader objects are used to customize the drawing behavior of many different kinds of nodes. If your shader needs to provide uniform data, you create one or more SK uniform objects. Okay. Compiling a shader and the uniform data associated with it can be expensive. You should initialize shader objects when your game launches, not while the game is running. You should avoid changing the shader's source or changing the list of uniforms or attributes while your game is running. Okay. Either of those things will recompile the shader. Share shader objects whenever possible. Okay. SK shader does not support OpenGL extensions. It will return an error if you compile a project containing a fragment shader using extensions. I don't know what that means. What is an OpenGL extension? OpenGL extensions are a means for OpenGL implementations to provide new or expanded functionality that the core of OpenGL does not provide. Using extensions should not be looked on as something to be avoided. Apple. It should be accepted as standard practice for the OpenGL user. Apple. SK shader. So why does Apple choose not to support OpenGL extensions? Does anybody know? I don't know why. Apple doesn't support OpenGL. But if Apple doesn't support OpenGL, what does this mean? An SK shader object holds a custom OpenGL ES fragment shader. Is it because of the word custom here? Meaning it's not real OpenGL? I mean, using metal, right? So maybe like converting the shader language to like metal shader. Is that what that is? Your GLCL is being compiled to metal shader under the hood and being run on metal. Yes. Okay. There you go. Makes sense. Okay. And I know nothing about metal programming. So this is all way out of my my comfort zone. Pretty cool though. Okay, so what did we gather from this? What we're getting is we have our shader. Your custom shader overrides the default shader, which neutralizes the default features. It is the responsibility of your custom shader to implement any of the features your sprites require. So what that means is that we cannot externally affect the color of the shader unless we treat it with uniforms, in which case in the shader code we would need to make some sort of like ability to mess with this color. So could I do this? Could I say color times equals vec3 of 0 red green blue 0 1, like this? Could I do that? And would that give me what I'm after? If I say, okay, no, this you're all going green, baby. Would that do what I want to do? Oh, I forgot a semicolon. Oh, man. Man, it's been a long time since I've had a semicolon error. I'll tell you what. There it is. Okay. So now we've got our green square, but I wanted a green border. I didn't necessarily, in fact, how can I make a shader with a clear color? I want a clear color shader. Background color. I want a clear background color on my shader, and anything that's not painted, I want it to be clear, not black. How would I do that? But don't we already have, like in our shader scene, didn't we say that our background color was clear? Filtering mode is nearest. Texture is texture. Shader test view. Our sprite views scene options allows transparency. Ooh, I might have to just because this paints the entire canvas from 0 to 1 in both X and Y. If I leave some pixels alone, that just marks them as black, right? Oh, wait a second. What if I did this? What if I did this? In my shader code, what if I said, listen, see, this is all 1.0. But what if I said 0.5 to get a little bit of opacity? Let's see what it would do then. Maybe I'd see something behind. You need to set the sprite view's background color to clear. Maybe. I feel like I had done that before, but I might not have. So let's just double check. Let's see. By doing this to 0.5. Ah, there we go. So now this, the unpainted, becomes 0.5. And this too it's green, but what if I do this? Then I probably won't be able to see anything, but let's just double check and see if that's if that does anything. I wonder. Well, ain't that something? So the painted area, in this case, the square, anything that was greater than 10% is exempt from this 0.0. So if this becomes clear by default, even if I put that in there, anything where this is true is going to show up, which is weird to me. Okay. So that's something. Just to answer your question, Cocotype, I believe that these options right here are what allow for the clear color in the sprite view. Oh, too much spice. Did I just like inhale too much of this sweet and spicy dust? What the heck? Not a sponsor, by the way. This is really good stuff, folks. Have you ever had this? But I clearly breathed it in. Okay. So what we're going to have to do is figure out a way to paint lines instead of regions, which is going to need to be, I think that's why they were pointing to using the smooth step instead of the step. Note that by changing values. Are you sure that's not a sponsor? I'm pretty sure. I haven't gotten any correspondence, so we'll see. It's the member of the Hormel Foods Extended Universe. The HMU. The HCU. The HEU. One of those acronyms will be accurate. Yeah, no, they haven't returned my my inquiry. That's bad. Okay. Now here's the thing. Let me look at this again. We have this 1 minus percentage times color plus percentage times vector 3 0 1 0. So if I add this is what causes that green line. What if I just did that? Ah. Okay. This is a family-friendly stream, Cocotype. Wait, hold on. Okay, mature content's not on. Okay, just wanted to make sure. So this little maneuver here, PCT is equal to plot. Again, this is like a series of smooth steps. I don't quite know what's happening here. This is all kind of voodoo magic for me still. This is you do a smooth step of whatever came in here, percent it minus 0.02%, st.y minus another smooth step. Learn more about smooth step. I would love to if whatever wasn't in the way. So let's do this again. You just know Matt and I are lurking around the corner ready to clip any incriminating thing you say. Yes. Yes. I've unashamedly kept those clips up, by the way. We got to be all real in this channel. And hopefully my voice doesn't give out because of terrible choices. Because I'm still kind of unsure about the smooth step function and seeing what that does. So I see that this is the case. So I see that a line is drawn. Jeez. Okay, what if I did this? Okay, what does smooth step even do? It performs smooth Hermite interpolation between 0 and 1 when edge 0 is less than x, which is less than edge 1. This is useful in cases where a threshold function with a smooth transition is desired. What if I just did this? What if I return sine of st dot y times percent? Okay, so that makes it like a gradient, but I lose that. Like I wanted to make like a sinusoidal line. I don't want a gradient. I want an actual line. So how do I do that? So we draw lines, which are just smooth step of 0.02 absolute value of st.y minus st.x. Plot a line on y. So how do I turn this into a sinusoid? And what this is plot sty, where I say pow. What if I do this? Sine times. Okay. So if this smooth step, if this is just what it is, plus st.y. So I can plot those by getting rid of this, just doing that. Okay, so I can make these curves using this sine function. And then I can yeah, but clearly I need to sorry, geez. That's gonna annoy me for the rest of the night. clearly there are some things that we have to okay. So I can mess with the starting point using like a mx plus b type thing. And then I'll say stx divided by 2 point. Maybe sine of. I'd like to get the full sine in there, please. Sine of s2 times x times 0.3 times 2 times 4. Okay. Times pi times 2 point. Okay, there it is. So what we're saying is this little method, this plot of vec2 st, which again st is just your pixel. You get to treat this like you're tracing a path along whatever function this is, which could be great. So instead of me doing this square thing where I was doing like a step function for the left and the bottom times the top and the right, what I would need to do is ooh, what if we did this? Hey, bro. Thank you for the sub. 23 months in a row. Holy smoke. 2 months. Let's go. Thank you, my friend. How you doing tonight? Welcome, welcome. Just playing with shaders today and just kind of doing the basics. It's going well. Learned a lot today. Learning all about building shaders. Still got a long ways to go, but found some really great resources online. thebookofshaders.com is what we've been using to learn here. Yeah, so like I feel like it's this step function is the way to go. Step will return 0 unless the value is over 0.5. In that case, it will return 1. What if we do STY? Oh, okay. Interesting. And then again, getting rid of this. So you've got these lines here and here. So you see what I did there? Then we can be like plus step. No, I think this is what I tried last time and it didn't work. Yeah, it didn't work. But if I did multiply, nope, that also didn't work. It also didn't work. We have all the way down here. We have here. Not here so much. Oh, was it going to be this? Oh, I know what it was going to be. It was going to be 1 minus 1 point dot minus. Nah, I broke it. is this where I get to do this step? No. See, this is only doing part of it. So it's almost like a trim function. Clearly, I've bitten off more than I can chew. So I need a lot of practice here. But I'm feeling encouraged by this. So that eventually when we build our shapes shader, maybe there's an easier way to draw arbitrary lines.
Just do it. Make your dreams come true.
Thank you. Yes, that is the goal. That is the goal. To just do it. So yeah, these curves, I would like to be able to like overlay them. But it turns out that I can't just add them together. There's something else that I'm missing here. So like a single function will work. But if I try to like just add like the reverse of that, it feels like it won't work. So like, for example, if I say plus, and then I'll just copy this and go I'll go from point 2 to point 8, for example. It doesn't like superposition. That's not the right word. It's not like a Z stack. So I still got to figure that out. But hey, we're getting there. Being able to make something cool like this, that would just be so cool. And we'll get there eventually. If it takes me another 2 years to figure out shaders, so be it. I'm going to be here for a while, folks. By the way, I'm coming up on 2 years as an affiliate. In fact, so if I go to it's like, I think later this month, I think I'll actually hit the 2-year mark. I've been streaming for longer than that. Of course, I had to stream for more types. Thank you very much. I appreciate it. Thank you. And I plan to keep on going. You know, I'm having a really good time here. And I just want to say thanks to everybody who keeps me company on this channel. And I appreciate your kindness and keeping chat nice and wholesome. Feels good. Just want to say thanks. It's been kind of a fun foray into this newfangled technology. It's been around for decades, but it's new for me. And also, I learned about this cool tool that is already available on all Mac computers called Grapher. So if you're feeling like you want to play with that, and you got a Mac, seems like a fun thing to try. I haven't really even come close to figuring out exactly how to play with it, but that's something that's available. Okay. How much time we got? Well, we're about ready to wrap up. I guess no games tonight. Also, I started a little bit late today, unfortunately. But I feel like we'll be doing some gaming on Thursday night. I'd like to finish Alan Wake. I still got probably 2 streams left for that. But if we could incorporate some of the shader stuff in our Swift UI game art, I think that'd be a really nice touch. Add some flair to it. Have you heard the story behind this app? No. What's the story behind this app? Grapher. Y equals sine of x. Boom, just like that. Pacific.com/story. The graphing calculator story. Basically, the people who developed it got let go from Apple, but they didn't want to give up, so they just kept showing up and tailgating people into the office and finished it up. Oh my gosh. That is a heartbreaking story, but very cool. That's amazing. That is really cool. Let's see. What did we get to? We got about to shape. Okay, so we were doing the rectangle stuff. Ooh, look at this, look at this, look at this. Okay, I scrolled too far down. We made it to rectangle. And then the next thing, okay, we're talking circles now. Okay. I think this is going to give me what I want. It's easy to draw squares on grid paper and rectangles on Cartesian coordinates, I suppose. But circles require another approach, especially since we need a per pixel algorithm. One solution is to remap the spatial coordinates so we can use a step function to draw a circle. Let's go back to math class. Sorry. Scroll too far down and woke a beast of shadow and flame. You know what they unearthed in Casa Doom. Where will you go? Oh my gosh, look at that. One of my favorite guns in Destiny is called Cartesian Coordinate. Nice. That's awesome. Look at this beautiful rendition. That is awesome. Okay, this is gonna tell us. It's giving us these recipes, man. I tell you, this is the site. It's a very nice solar fusion rifle. Excellent. Have you beat all the raids, bro? All the way up to the Witch Queen? Is she dead and gone? All right, how do they fix it? You've cleared everything there is, bro. That's awesome. Way to go. New season just started, a new dungeon and holiday event. Oh, that's cool. That's awesome. Wait, when I played with you guys, was it during Halloween or was it during like the winter event? There's a new expat coming in March. Gosh, time flies. Jeez. It's gonna have a Sherpa rating system. I'm super excited for it. Oh, I'd like to hear more about that. I think it was Halloween. Man, that was so long ago. That was 2 Halloweens ago, right? I think it's like the Overwatch commendation system. Oh, that's cool. So if you're like able to like help out new players and stuff, or is it just like an overall like group thing? Each square on the grid paper is a pixel. It implies asking each pixel or if it's inside the area of the circle just by computing the distance from the pixel to the center of the circle. Oh, okay. There's several ways to calculate. The easiest one uses the distance function. Distance. So you have a twin distance. I see. Percent is distance st vec2 0.5. Oh my gosh. Just like that. And you get, there's your circular gradient. You and your buddy do lots of Sherpa, new people to new activities. Oh, that's cool. Or something similar, I think, to the FF14, I think, or like you can like a veteran player can like do like low level dungeons and get like additional XP for that. This is what we need right here. Look at this. Now, geometric shapes can be defined very easily in terms of like mathematical functions. So like this is the kind of cool stuff that like we're looking at here, right? So like you have your position, you have your arctangent of whatever y and x you're at, which gives you your a, and then you do a cosine of a times that, and that gives you the value. Gosh. Yeah, guys, I think I might be spending some more time in Shaderland. Definitely not giving up on SwiftUI shapes and paths, but I'm very much interested in expanding my my domain knowledge here. Okay, they talk about polar shapes. Okay, I keep on accidentally scrolling too far down. Okay. What time are we at? We got just a few minutes. Distance function, which internally computes the length of the difference between 2 points between the center of the canvas and whatever coordinate we're at. The length is nothing but a shortcut of the hypotenuse equation that uses square root internally. Okay. You can use distance or length or square root to calculate the distance to the center of the billboard. When a release of Windows version is part of Windows 98, but sadly Microsoft has effective building security. I gotta read that whole article, Kogotai. That's awesome. They were seriously like using the open door to like just sneak in and finish writing the program. That is something. That's crazy. The following code contains these 3 functions and the non-surprising fact that each one returns exactly the same result. So you could use distance, you could use length, or you could use square root, and you'll get all of them. So you got your fragment coordinate XY, so you got your vec2, float PCT, the distance of ST and vec2 0.5. The reason why this works is because vec2 with a single argument, 0.5, means you're doing 0.5 in X and 0.5 in Y. So you're doing the distance between whatever we are and there. That's your percent, and then your color is going to be, it's all in grayscale, so you're going to be RGB of all the values of the distance. So for greater distances, you have smaller values? Oh, sorry, no. For smaller distances, you have smaller values, which is why it's black in the center and it approaches white in the corner. That makes sense. Okay, so let's try copying this and remaking it here in our Swift stuff. I'm gonna stop. I'm gonna go back to my SHK water, and I'm going to just do that. I'm calling you main2. So you're going to be vtex chord. And this should do it. Yeah, it looks like the distance method is observed in the Swift shader language. Just kidding. Error, use of undeclared identifier interpolated. Wait, what? Void function main2 should not return a value. Oh dear. It's oh, I see. Okay, so if I just comment that out, then maybe it won't be mad at me. Interesting. Okay, so lesson learned. Don't. There it is. So the distance between the center, which is 0.5, and my ST, which these are all these are normalized. So VTEX chord is a normalized pixel, which is great. You're getting closer there. If we did 2 times this, then maybe it would be all white here instead of gray. Let's try that. There it is. Okay. Wow. What a fun exploration. Folks, it's time for me to go to bed. I've been going to bed way too late this week. I need to catch up on some hours. And wow, I'm really excited about this. I found a great resource. Again, let me paste the link. If anybody else is interested in this stuff, it's called thebookofshaders.com. And this'll if you're interested, this is available. The shader language, you can do it in your browser and test with this. It's a lot of fun. Thank you, bro, for the shout outs with the GitHub and the Discord. Please, if you like what you see, come on back. I stream every Tuesday, Thursday, and Saturday from 8 to midnight Pacific time. We have a nice cozy Discord that a lot of friendly people in there, just building each other up, and it's fun times. So hey, we'll see you next time, and so long.